Welcome to DAR Tutors for online and home tuition. Today, we're going to dive into the first part of our series on graph theory, a fundamental topic in IB mathematics applications and interpretation HL. Our primary objectives for this lesson are to introduce the core concepts and terminology of graphs, and to explain how to represent and analyze simple networks. By the end of this video, you will be able to define key terms like vertices and edges, classify different types of graphs such as undirected, directed, and simple graphs, and construct and interpret adjacency matrices for representing network connections. We'll begin with an opening problem to illustrate the practical applications of graph theory. Imagine Evan and Heidi are visiting Paris. The map shown here illustrates their hotel, various landmarks, and the roads connecting them. This entire structure is a graph. Evan's goal is to visit each landmark exactly once and return to the hotel. This is a classic problem in graph theory known as finding a Hamiltonian cycle. Heidi's goal is different. She wants to walk along each road exactly once, also returning to the hotel. This is the problem of finding an Eulerian circuit. The fact that these two seemingly similar questions lead to very different types of mathematical problems is what makes graph theory so powerful for modeling real-world scenarios, from optimizing travel routes to scheduling complex projects. Let's begin by formalizing the terminology we'll use throughout our study of graphs. Think of a graph as a mathematical structure that shows how things are connected. The first key component of any graph is a vertex. Vertices, also known as nodes or points, represent the things of interest in our network. These could be towns, airports, people, or in our Paris example, landmarks. Next, we have edges. Edges are the connections or relationships between these vertices. They are represented by lines and show that two vertices are related in some way. In our map, edges represent roads. In a social network, an edge might represent a friendship. Edges are named by the vertices they connect. For example, the edge connecting vertex A and vertex B is simply called edge AB or BA. Sometimes, an edge might connect a vertex back to itself. This special type of edge is called a loop. Now, let's consider a practical problem using this terminology. Imagine a communication network. Here are the components: a server, 7 computers, a modem, and 2 printers. Our objective is to draw a graph that represents this network. For simplicity, we can group common components together. We'll represent the server as vertex S, the group of 7 computers as vertex C, the modem as vertex M, and the 2 printers as vertex P. Now, let's add the connections, or edges. The notes tell us the 7 computers are connected to the server, so we draw an edge between C and S. They also state the server is connected to the modem, so we draw an edge between S and M. Finally, the server is connected to the 2 printers, so we draw an edge between S and P. This graph now visually represents the structure of the communication network. So, we've now defined vertices, edges, and loops, the fundamental building blocks of graph theory. We've also applied this terminology to construct a simple model of a communication network. Graphs can be divided into several categories based on their properties. Let's start with the most common type. An undirected graph is one where the relationship between vertices is symmetrical. If there's an edge from A to B, you can travel from B to A just as easily. Think of a two-way street or a mutual friendship. For undirected graphs, we introduce the concept of degree. The degree of a vertex is simply the count of edges connected to it. A key rule to remember is that a loop on a vertex contributes 2 to its degree. Let's see this in an example. Consider this undirected graph. Let's find the degree of each vertex. Vertex A has 1 edge, AB, so its degree is 1. Vertex B has 4 edges, BA, BC, BD, and BE. Its degree is 4. Notice that A and B are adjacent because there's an edge connecting them. Vertex C has 1 edge, BC, so its degree is 1. D has 1 edge, BD, its degree is 1. E has 2 edges, BE and EF, so its degree is 2. Finally, F has 2 edges, FE and FD, so its degree is 2. Now let's look at the other main category of graphs. A directed graph, also known as a digraph, has edges that can only be traveled in a specific direction, indicated by an arrow. Think of a one-way street or a mentor-mentee relationship. Because direction matters, we have 2 types of degrees for digraphs. The in degree of a vertex is the count of edges pointing into it, while the out degree is the count of edges pointing out of it. Let's find the in degree and out degree for each vertex in this directed graph. Vertex A has one incoming edge from B and one outgoing edge to B. So its in degree is 1 and its out degree is 1. Vertex B has two incoming edges from A and C and two outgoing edges to A and D. So its in degree is 2 and out degree is 2. We have now distinguished between undirected and directed graphs and learned how to calculate their respective degrees. These concepts are foundational for understanding how to navigate and analyze networks. Beyond just direction, there are other important properties that define a graph's structure. Let's start with the concept of simplicity. A graph is considered simple if it has two specific characteristics. First, it must contain no loops, no edges connecting a vertex to itself. Second, there can be at most one edge between any two distinct vertices. Most graphs we'll study are simple, as they are easier to analyze. Next, let's discuss connectivity. An undirected graph is connected. If it's possible to start at any vertex and travel to any other vertex by following the edges. If this isn't possible, we say the graph is disconnected. A disconnected graph consists of several separate components, like islands. For directed graphs, the concept of connectivity is a bit stronger. A directed graph is strongly connected if there is a path from every vertex to every other vertex, respecting the direction of the edges. It's not enough to be able to reach B from A. You must also be able to reach A from B. This is a very robust property, common in networks like the internet. Let's work through an example. Determine whether this directed graph is strongly connected. To do this, we need to find a path from every vertex to every other vertex. Let's start from A. Can we reach everything? Yes, A to B, B to C, C to D. From D, we can go back to A or to B. From B, we can go to key D or A. It seems every vertex is reachable from A. Now let's verify the other direction. Can we reach A from every other vertex? From D, we have a direct path DA. From C, we can go CDA. From B, we have BDA. Since we can find a directed path from any vertex to any other vertex, this graph is indeed strongly connected. We have now seen the properties of simple, connected, and strongly connected graphs, which are essential for describing network structures. So far, we've used diagrams to visualize graphs. While intuitive, diagrams can become cluttered for complex graphs. A more formal and systematic way to represent a graph is through an adjacency matrix. An adjacency matrix is a square matrix where both the rows and the columns are labeled with the vertices of the graph. The entry in row I and column J tells us the number of direct connections from vertex I to vertex J. Let's construct the adjacency matrix for this undirected graph. First, we label the rows and columns in alphabetical order. A, B, C, D. Now we fill in the entries. For A to A, there are no loops, so it's 0. For A to B, there is one edge. For A to C and A to D, there are no direct edges, so they are 0. Since the graph is undirected, the connection is mutual. So if A to B is 1, then B to A must also be 1. The matrix will be symmetric. Completing the matrix, we get the adjacency matrix A. Let's look at the entry in row C, column D. It's 2. This means there are two edges connecting C and D. Let's verify, and yes, there are two distinct lines between C and D. Now let's construct the adjacency matrix for this directed graph, with vertices in order P, Q, R, S, T. This time we cannot assume symmetry. Let's fill it out. The P row shows connections from P. P goes to S and T, so PS is 1, PT is 1. The Q row shows connections from Q. Q only goes to R, so QR is 1, and so on for each row. The resulting matrix, A, is the adjacency matrix for this digraph. Notice that it's not symmetric. For example, Q to R is 1, but R to Q is 0. We've now learned how to convert a visual graph into a structured numerical adjacency matrix. This representation is a powerful tool, as it allows us to analyze complex network properties using the tools of linear algebra, which we'll explore next. So we have this wonderful new tool, the adjacency matrix, A. It's great for showing us the direct one-step connections in a graph. But what if we want to know about connections that require multiple steps, like traveling from Paris to another city with one stop? This is where the true power of adjacency matrices reveals itself. If you multiply the adjacency matrix by itself, that is, you calculate A squared, the resulting matrix, A squared, is an adjacency matrix for all the two-step routes. A is the adjacency matrix for one-step routes. Then A squared is the adjacency matrix for two-step routes. A cubed is the adjacency matrix for three-step routes, and so on. Let's work with the example graph from our notes. Its adjacency matrix, A, shows the direct flights between cities. If we calculate A squared, we get this matrix. Each entry A squared subscript ij now represents the number of flights that take exactly 2 steps to go from city I to city j. For example, the entry in row 1, column 3 is 2. This means there are two two-step routes from city A to city C. Now, why does this work? Let's take a look at the matrix multiplication that creates this entry. The entry in row I, column j of the product of two matrices is found by taking the dot product of row I of the first matrix and column j of the second matrix. Let's say we're calculating the entry A squared subscript ij. The dot product involves terms like A subscript I multiplied by A subscript kj. This term represents the number of one-step routes from I to k, multiplied by the number of one-step routes from k to j. If both values are 1, it means there's a route from I to k and a route from k to j, forming a two-step path. We sum this over all possible intermediate vertices k. In essence, we are counting all possible intermediate cities that can connect our starting city I to our destination city j in 2 flights. This process is precisely how matrix multiplication counts multi-step routes. Let's confirm this for our example. We have two two-step routes from A to C. By looking at the original graph, we can see these 2 routes: A to B, then B to C, and A to E, then E to C. This confirms that A squared successfully counts the number of these two-step journeys. To find all routes of n steps or less, you can sum the powers of the matrix up to n, A plus A squared plus A cubed, and so on. A 0 in the final summed matrix indicates no route of that length or less. Understanding graph theory is more than just calculations. It has profound implications for how we perceive and interact with the world. Consider Henry Beck's 1933 redesign of the London Underground map. Beck, a technical draftsman, understood that for a traveler on the underground train, the geographic distance or the precise curves of the tunnels were irrelevant. What truly mattered were the connections between stations. He replaced a geographically accurate, cluttered map with a schematic diagram. He straightened the lines, equalized station spacing, and used only horizontal, vertical, and 45-degree diagonal lines. He essentially stripped the map down to its underlying graph. His map was a revolutionary application of graph theory. Its primary function was to show connectivity, not topography. This design made the complex network understandable and navigable, transforming urban transport forever. Other cities like Sydney and Copenhagen adopted similar designs for their metro systems. This example highlights a critical distinction we must make in graph theory. An adjacency matrix tells us how many routes of a certain length exist between vertices. However, it doesn't distinguish between a good route and a bad one. The matrix A cubed might tell a salesman there are 3 three-step routes from A to B, but one route might be A to C to D to B, which visits 3 different places, while another might be A to B to A to B, which is a repetitive and inefficient detour. The matrix A cubed doesn't just count paths, it counts walks. For a salesman, a walk that backtracks is not useful. He needs a path. This is a key limitation. We use the terms walk, trail, path, circuit, and cycle to describe routes with increasing restrictions to handle these nuances, concepts we will explore in detail in a future lesson. Let's work through some more complex problems to solidify these concepts, which align with the IBAI-HL syllabus. Here's a problem involving a board game. A counter can move horizontally or vertically to an adjacent square. We need to construct the adjacency matrix A for this game. First, we list the vertices in order. A, B, C, D, E, Phi. Then we create the 6 by 6 adjacency matrix. This is an undirected graph, as movement is two-way. Now, the problem asks us to determine if it's possible to move between any two squares in at most 2 moves. This requires us to look at the adjacency matrix for 1 and 2 step moves, which is A plus A squared. If we calculate this matrix, A plus A squared, we find there are several zero entries. For example, the entry for C to D is 0. This means it's not possible to get from C to D in 1 or 2 moves. So, no, it's not possible to move between any 2 squares in at most 2 moves. What about at most 3 moves? For this, we need A plus A squared plus A cubed. After calculating this sum, we find that every single entry in the matrix is non-zero. This indicates that a counter can travel from any square to any other square in at most 3 moves. This shows how we can use matrix operations to answer complex questions about network reachability. We've covered a lot of ground today. Let's recap our key takeaways. We started with the basic building blocks, vertices to represent objects, and edges to represent connections between them. We then classified graphs based on the direction of their edges, leading to undirected and directed graphs, and defined how to measure their connectivity using degrees. We also learned about important properties like being simple, connected, or strongly connected. Most importantly for IBAI-HL, we introduced adjacency matrices. We saw that an adjacency matrix is a powerful algebraic representation of a graph. Furthermore, by taking powers of the adjacency matrix, we can determine the number of multi-step routes between any 2 vertices. We used these matrices to analyze network properties, like the reachability of squares in a board game, confirming that we have met our learning objectives for this session. You can now define graph terminology, classify various graph types, and construct and interpret adjacency matrices. Now, to help you prepare for your IB exams, here are a few practice questions that test these concepts. Pause the video, try to solve them on your own, and then continue to see the worked solutions. Welcome to DAR Tutors. If you're looking for expert tuition in IB A-level or IGCSE curricula, we are here to help you achieve your academic goals. Our team of experienced tutors provides personalized online and home tuition tailored to your specific needs. Contact us today to learn more and schedule your first session. Now let's get back to our practice questions. Here is your first practice question. You are given a directed graph. Your task is to find its adjacency matrix, which we'll call A, and then calculate A squared. Pause the video here and try to solve it yourself. Welcome back. Let's work through the solution. First, let's find the adjacency matrix A. We order the vertices A, B, C, D. Vertex A has an arrow pointing to C. B has an arrow to A. C has arrows to B and D. D has an arrow to A. This gives us the adjacency matrix A. Now for part B, we need to calculate A squared, which represents the number of 2-step walks. We perform matrix multiplication, A times A. This yields the matrix A squared. Let's interpret A squared. The entry in row A, column B is 1. This tells us there is one 2-step walk from A to B. We can verify this on the graph. A to C to B. The entry in row B, column C is 1. One 2-step walk from B to C, B to A to C. The entry in row C, column A is 2. This means 2 2-step walks from C to A, C to B to A, and C to D to A. Great job if you got this right. Question 2 introduces a new concept, a plus A squared. This matrix represents the total number of walks of length 1 or 2 between any 2 vertices. The question asks for the meaning of the 0 entry in row E, column D. Let's first find A and A squared for this graph. Here are the adjacency matrix A and its square A squared. Next, we calculate the sum, A plus A squared. This gives us the total adjacency matrix, containing walks of length 1 or 2. Now let's answer the question. The entry in row E, column D is 0. This means there are 0 walks from vertex E to vertex D that are either 1-step or 2-step long. If we inspect the graph, we can confirm this. From E, we can only go to B. From B, we can only go to D. So the only way to get from E to D is EBD, which is a two-step walk. But wait, our matrix says 0. This is a crucial point that tests our understanding. The graph I'm showing you is different from the one in the notes. Let's solve the original problem. Here's the correct graph. Its adjacency matrix A and A squared are different. The total adjacency matrix, A plus A squared, also has zeros. For example, the entry for row E, column C, is 0. This means there are 0 walks of length 1 or 2 from E to C. Let's verify on the graph. From E, there's a one-step walk to B. From B, there's a two-step walk to C, B, AC, or BDC. Therefore, a 0 in A plus A squared implies there are no walks of length 1 or 2. In this case, we have a walk of length 3, EBDC. A very important distinction to keep in mind for your exams. Let's move on to the third practice question, which builds on the concepts of adjacency matrices and multi-step walks. The problem gives us the adjacency matrix A for a directed graph with 5 vertices. We need to find the number of two-step routes from vertex Q to vertex S, the number of three-step routes from vertex P to vertex R, and interpret the significance of A cubed plus A. Let's begin with the first part. How many two-step routes are there from Q to S? To find two-step routes, we need A squared. This matrix contains the number of all two-step routes. The entry in row Q and column S of A squared is 2. Therefore, there are two two-step routes from Q to S. These routes are QPS and QTS. Next, how many three-step routes from P to R? For three-step routes, we need A cubed. The entry in row P and column R of A cubed is 1. So there is one three-step route from P to R. The route is PSTR. This is a path. Finally, part C asks for the significance of A cubed plus A. The matrix A counts one-step routes, and A cubed counts three-step routes. Therefore, their sum, A cubed plus A, will give the total number of routes of length exactly 1 or exactly 3. For instance, the entry in row P column S of this new matrix is 1. This means there is only one route from P to S that is either one step or 3 steps long. In this case, it's the direct one-step route, P to S. Well done if you could distinguish between the meanings of these different matrix operations. Our fourth question is a bit more open-ended and requires a clear, reasoned explanation. The question asks if it's possible to create a directed graph with 4 vertices where vertex A has an out degree of 3, vertex B has an in degree of 3, and all other in degrees and out degrees are less than or equal to 1. Explain your answer. This question is about applying a key theorem in graph theory. Remember, each edge in a directed graph contributes exactly 1 to the total out degree and 1 to the total in degree. This means that the sum of all in degrees in a graph must be equal to the sum of all out degrees. This sum is simply the total number of edges in the graph. Now let's apply this to the problem. We have 4 vertices, A, B, C, D, E. Let's calculate the minimum possible sum of out degrees. We are told the out degree of A is 3, and the out degrees of B, C, and D are each at most 1. So the minimum total out degree is 3 plus 0 plus 0 plus 0, which is 3. The maximum total out degree is 3 plus 1 plus 1 plus 1, which is 6. Now let's do the same for the in degrees. The in degree of B is 3, and the in degrees of A, C, and D are each at most 1. The minimum total in degree is 0 plus 3 plus 0 plus 0 equals 3. The maximum total in degree is 1 plus 3 plus 1 equals 6. So the total number of edges, which must be equal to both the total out degree and the total in degree, must be between 3 and 6. The question is whether such a graph must exist. The theorem only guarantees that if a graph has edges, the sums will be equal. It doesn't guarantee that a graph can be built for any arbitrary degree sequence. So the final answer is no. The fact that the sums can be equal doesn't mean it's possible to draw the graph with those specific vertex degrees. For our final practice question, we'll return to the bus service problem. We have a graph of a bus network. The bus company wants to ensure people can travel between any 2 towns in at most 2 trips. They need to find a service to cancel. First, let's find the total adjacency matrix for at most 2 trips, A plus A squared. After finding the adjacency matrix A and calculating A squared, we find that the sum A plus A squared contains no zeros. This confirms that currently, it is possible to travel between any 2 towns in at most 2 trips. Now for part CI. The company considers canceling the service from C to D. We need to show this won't achieve their aim. If the C to D service is canceled, we update our original matrix A, setting the entry in row C, column D to 0. Then we recalculate A squared and the sum A plus A squared. The new total adjacency matrix now contains a 0. Specifically, the entry in row B, column C is 0. This means it's no longer possible to get from town B to town C in at most 2 trips. For example, B to A to C is a 2-step route that still exists, but the matrix now reflects the loss of the direct service from B to C. So canceling C to D is not a good idea for the bus company. Finally, for part C2, we need to find a service that can be canceled without losing the 2-step connectivity. A service can be canceled if it is redundant for the 2-trip aim. This means there must already be a 2-step route that covers the same connection. A good candidate for removal is the direct service from B to D. The original matrix A has a 1 here. Let's check A squared. The entry for row B, column D is 1. This means there's already a 2-step route from B to D, B to A to D. This makes the direct B to D service redundant. If we remove B to D and recalculate A plus A squared, the resulting matrix still has no zeros. So the bus company could cancel the service from B to D without failing to achieve its 2-trip aim. This is a perfect example of using matrices to make optimal decisions. This concludes the first part of our introduction to graph theory. We've established a solid foundation with key definitions, graph properties, and the powerful application of adjacency matrices. We encourage you to revisit the concepts and practice the exercises from your textbook. In our next videos, we will build upon this foundation to explore more advanced topics, including the famous Hamiltonian and Eulerian paths and circuits that Evan and Heidi were looking for in Paris. Thank you for watching. For expert guidance and personalized tuition to help you master these concepts and excel in your IB, A-Level, or IGCSE exams, visit our website at dartutors.co.uk. We look forward to helping you succeed.